She's one of the leading world caliber person in ground motion. She was previous president of Seismological Society of America, played many important roles. And thank you for being involved in this game.
Oh, well, thank you. And yeah, Norm really needs no introduction. He's, I would say, in my view, I think he's probably the leading expert in ground motion and how it's applied in a very practical way to seismic hazard evaluation. And so I think you've all heard the expression, the new normal, and today I'm the new norm. So I'm going to do my best to challenge my inner norm, or channel that inner norm, but at the same time take advantage of this unique opportunity to make Norm say whatever I want him to. So without further ado, Norm was kind enough to send these slides yesterday, with his apologies for at the last minute being unable to make it. And what I'll be focusing on is the need for RuFZO to improve seismic hazard estimates. And so this is really all about uncertainty in seismic hazard. And the seismic hazard estimates are all driven by two main components. There's a source model and a ground motion model, or a GMM. And if we're looking at areas near active faults, the source model is something that we typically already have some information on. We have fault-specific data, such as slip rates and so on. And so we know something about the source. In fact, we know enough about the source to kind of have a handle on its gross properties for specific sources. But for ground motion models, on the other hand, these are typically based on global models over wide distributed regions. And they give us very good stable average estimates of median ground motions as a function of a few gross parameters. But what we don't have are specific source, path, site information that's embedded in that ground motion model to the same extent that even a gross model of the source gives us. So we end up with median ground motion models that could be potentially biased. And we have a lot of the variability from event to event, path to path, that should actually be governed by physical models that instead we've casted into this big thing called aleatory uncertainty or random scatter, because we don't know any better. And so that is what we can really grab onto in ground motion models and improve. And we specifically can improve that ground motion accuracy if we can get that specific information on source, path, site. And to do that, we need to move towards making better use of three-dimensional simulations, and also moving towards so-called non-ergodic, meaning more specific ground motion models. And why do we want to do that? Why is that important? And what's the sort of motivation? The rationale is that the epistemic uncertainty in these ground motion models, because they're so gross and broad, are what's really driving the epistemic uncertainty in seismic hazards estimates. And that's a really big deal. It has huge implications financially in the many hundreds of millions of dollars. And so that's the rationale for focusing on ground motions when we're thinking about one of the sort of practical benefits of RuFZO, as well as learning a lot more about earthquake physics. So how can RuFZO improve ground motion models and also our simulations? A number of ways. Let's talk very briefly first about the source. Currently, when we're working on these non-ergodic or path and site-specific ground motion models, we're using small magnitude data so that we can essentially improve the sampling of ground motions. We get a lot better coverage of our ray paths and our site terms. And we can also learn more about the source in those small magnitude data. But we run into a problem that I've highlighted at the bottom of the screen here, where we have a question that seismologists have been puzzling over for decades that we don't have an answer to. And that is, what do those region-specific or event-specific source terms from the small magnitude data really tell us about the corresponding source terms from larger magnitude events that we would really like to be able to model better. And to make progress in answering this, we really need the data from RuFZO so that we can test how source scaling works from that small magnitude data that we're collecting while we're waiting for larger events to larger events. And also, this provides a rationale for looking at multiple faults, because we don't suppose that this scaling is necessarily the same for every fault that we're going to look at. Path effects in non-ergodic ground motion models are a really big thing that RuFZO will definitely help with. Right now, what we do in current non-ergodic ground motion models is we simplify the path effects of finite ruptures with very simple metrics, like what is the closest distance from the observation point to the fault rupture plane. And we can use 3D simulations to test how well that assumption works and provide alternative models that might work better. Are there better ways that we can represent the path from the rupture to the observation point? And we need observed ground motions from the small events along the rupture plane of the larger event in order to evaluate how well those approaches work. We can use observed ground motions over quite broad period ranges to look at how we can model those path effects. And to do that, we need a much denser spatial sampling than we have in current ground motion sets. Right now, despite having that wonderful network that Bill pointed to in his talk, it looks great when you look at it when you're looking at a map of the entire state of California. And it looks like, oh my goodness, we've got a seismometer everywhere. They're as plentiful as the dots on the carpet. But when you actually go down and zoom in, you find out that what looks like carpet it looks like you've carpet bombed the entire state with ground motion instruments. But when you get down close, you find out that when you're stepping near to a fault, suddenly you look around and you don't see a seismometer anywhere. They're tens of kilometers or 5s of kilometers away. And so that's what we really need to get in order to better understand these path effects on a very fine scale, is we need to have the instruments that are spaced like the dots on the carpet here. Evaluation of ground motion models. Right now, the common ways that we use to evaluate ground motion models, and Anne-Marie touched a little bit on this in her talk, is we look at residuals. We look at the differences between our predictions and our observations. And that's a very crude way. It's the best we've got at the moment, but it's kind of a crude way of looking at how the models differ from the observations. And we try and break that down into components, as Anne-Marie was describing: path, source, and site. But if we had denser observations, then we could move that evaluation to more formal procedures that are more similar to, for example, what's been used for the evaluation of earthquake prediction models, more formal evaluation procedures that would truly give us better insights into how well our ground motion models were working. And we can use the data from RuFZO and indeed its framework to evaluate ground motion models and simulations using a whole variety of methods that require different inputs. And to do that, we're going to need three-dimensional velocity structures for simulation models. And we're going to need non-ergodic ground motion models that are going to require empirical data. And those, for those methods to work, we're going to need the more detailed data that RuFZO can provide. There's a whole bunch of classes of ground motion methods that we can potentially evaluate, and I don't think I'm going to go into this in any detail, but there's all kinds of different empirical techniques. Machine learning techniques are really starting to come online in ground motion modeling. And then, of course, there's simulation. based techniques where we develop models based on simulations, either 1D velocity models or more detailed 3D velocity models using things like CyberShape and so on. So one of the key questions that that we want to ask when we're evaluating ground motion methods, and I know this is something actually Norm has talked about a lot, is do those more complex methods, if we put in 155 parameters in our ground motion model, do we actually get a more accurate prediction than if we use only 4 parameters? Do those more complicated models do a substantially better job at predicting ground motion models than the simple models? If the answer is no, why would we bother? You know, we just stick with the simple models and we don't need all of those extra parameters. Of course, the more parameters you throw in, the better is your ability, fewer degrees of more degrees of freedom. You can model anything if you have, you know, enough parameters. But it's also important to ask, well, how many of those parameters are we going to be able to predict in advance? How transferable from this situation to another, and so on. And so I think one of the really important things we can evaluate with the RuFZO data is this key question of how do simple models compare with complex models, and what's the right balance in model complexity. Another important question in terms of evaluation is, does the epistemic range from the current ground motion method that we're using, whatever that is, does it capture the median of the observed ground motions for any specific site, path, source combination? Because that's what our epistemic or our model uncertainty is supposed to do. It's supposed to cover that whole range. And if it's not doing that, and we've seen so many earthquakes where that happens, oh, here's another unusual earthquake, just like the last one was unusual. And it kind of tells us that for most of our simplified ground motion models, that's not really the case. And similarly, our 1D simulations are taking what are really systematic events and mapping them into aleatory uncertainty. And that's one of the things that we can, I think, really improve upon with RuFZO. So what all can we get while we're waiting for for a large event? And I think actually anything magnitude 6 and above is actually a large enough event that we're going to get substantially new information. And so here are a number of interesting exercises to do while waiting. First of all, that's the perfect time to make blind predictions of what the ground motion spatial distribution will be for a whole suite of different scenarios, using whatever is the available data, the models, the ground motions, the simulations, and so on, and computing a whole bunch of metrics. So let's start working, as soon as those instruments are in the ground, let's start working on making those blind predictions. What do you expect to see for these different types of earthquakes? And just getting different modeling teams working on those will provide a lot of benefit, because those modelers all talk to each other and there's feedback, and they get together in workshops like this and they all sort of learn to fine-tune their models. During that time, we can be working on coming up with what are the rules for applying the ground motion models to estimate. You know, if you don't make the rules in advance, it's really easy after the fact. Once you know the answer, it's way easier to get the answer when you know what the right one is. We've all had that experience. And so you have to decide in those rules, what are the event-specific information really that you're going to use for each one of the models. It should be something that's limited enough that you can reasonably specify that in advance of earthquakes. Very simple things like the magnitude, the mechanism, maybe the rupture geometry, the depth, and so on, things that you might be able to specify in advance. Part of the input to this whole thing is going to be the 3D velocity structure. That's something that you can put as part of the input. And then after an event occurs, SCEC will be able to implement all of those fixed models for testing and evaluation. And another, I think, really interesting thing is if we've got these instruments in the ground and they might be there for a decade, 2 or 3, who knows how long, while we're waiting for that big event to happen. But because we're gathering all of that small magnitude data in the interim, those models should presumably be getting better every year or 2. So get those groups working, get them making their blind predictions, and then every 2 or 3 years, get them to update them with the new data that they've gotten in the last 2 years. And, you know, what comes to mind for me when I think of that is versioning. So you would have every few years, you'd have version 2025, version 2030, and so on. And then when the actual big earthquake happens, not only can you look at how well the models do versus each other, but you can also look at how the improving information at the small magnitude level, did that do a better job or not? And to me, that's a really interesting question. Which faults? That's something we're going to talk about a lot in the discussion. The best answer, of course, is all of them. But if we can't do all of them, one of the questions that actually I asked Norm, that was sort of from a practical viewpoint. What my thinking was, if we cite some of the RuFZO instrumentation near high value or critical infrastructure, will that help get us funding for this whole thing? And his answer was quite interesting. He said probably not. And the reason is that while that would provide data that could be used directly for those types of infrastructure, there would be concerns about having it publicly available. And so instead, Norm's suggested alternative is that what would be done instead is people could build test structures, scale models of things near these faults, and use those to gain information that would be equivalent but less controversial. The other thing that he mentioned was that it is also better to simply use the results of RuFZO to show the improvement in the accuracy of seismic hazard estimates, and use that as a way of convincing owners of such critical infrastructure to put in instruments near their sites. The common view, and I think we've mentioned this a lot this morning, is that they have to wait too long for a large magnitude earthquake. And so that's something we need to stress over and over again, is how the recordings from the small magnitude events while you're waiting for the big one give you a lot of value added and help with the simulations and so on. And then another question that I asked Norm is there a particular location for RuFZO that would fit with current efforts that are ongoing, that Norm is doing a lot of work leading on developing non-ergodic ground motion models in the state of California? And, he points out that one of the big issues in developing those models is this trade-off between path and site effects. You need to get sources being distributed enough so that you're sampling multiple azimuths. If you've just sort of got all the sources in one place, then you end up with a non-uniqueness problem in separating the path and the site effects. So it's one good idea is to look not just at specific faults, but places where there are nearby neighboring faults, so that you can get a sample more of a variety of path and site effects. And obviously, the more faults you sample, the better. So it's good that we're talking about not just the Southern California, but also Northern California faults like the Hayward, Calderas, and looking at putting, even for the San Andreas, let's make sure that we don't cover just the Northern San Andreas or the Southern San Andreas, because wouldn't it be a shame if we guessed the wrong one? So those are things to think about. And so that's about it. So to basically just summarize those issues that are most important for seismic hazard that RuFZO can address. Region-specific source terms from small magnitude events. What does that tell us about source terms for large magnitude events? Can we use the path effects that we can measure at short periods to accurately model non-ergodic ground motion or 3D simulations? And finally, how much do more complicated non-ergodic ground motion models, simulations, and so on, how much added value do those give us for seismic hazard relative to more simple models? And how can we formally evaluate that? So with that.
We didn't get for stepping in for Norm. That was excellent. Maybe one quick question. We're running a few minutes behind schedule. Can we have one question and then maybe take a bio break and then we get into the discussions? One question. Burning. Yeah.
I know you had mentioned trying to use like test structures near them. Are people doing that right now?
Apparently, yes, there are several places, and I gather Parkfield is one of them, where there's been like scale models to like about 1/12 of the scale for things like nuclear containment structures, putting them there. And so to me, that would be a really intriguing thing and a really great way to get engineers involved because they really like to break things. So if you put, you know, invite people to come and build little structures near these faults and near the observatory. And I think it's a great suggestion that Norm has made in this regard, because it does kind of side skirt that controversial question of does anybody really want to know what the ground motions are near the real nuclear power plant?
Has it led to any more seismometers or any testing being implemented? Or
that's a really good question, and I'm not sure I entirely know the answer. I think it probably has to some extent, because I know that there are some of the larger utility players like PG&E that have actually, you know, invested pretty heavily in those types of ventures. But if Norm were here, he could give you a much better answer.